Hi everyone, good evening. Welcome to Amrita JEE Crash Course. And this is chemistry class. And we will be discussing very few interesting topics in chemistry. I hope everyone is excited. Those who all attended the previous class must be knowing what is going on in this crash course. Correct? Those who are joining today's class, so please focus. These are completely new concepts for this crash course. Okay, shall we start? I hope all of you are ready to learn new concepts in chemistry, correct? So if there is any issue like any audio issue or video issue, please let us know. Okay. And is it clear? Or I'm zooming it. The question on the screen, is it clear? There is no audio delay, video delay, right? There's no problem, right?
Nothing, sir. It's clear.
Okay, fine. Thank you. Okay. So we'll start. We'll start with this question today. Question is about volume strength of 1.5 normal H2O2. See, H2O2 solution is where we use H2O2. Anybody knows this? Hydrogen peroxide. No? Where do we use this? Hydrogen peroxide. Any idea? Voice is very low. Is it like that? All right. Yes. H2O2. This chemical, no, in daily life, do we use this? Yes, no, it is used in hair bleach. Okay, very important chemical in hair bleach is hydrogen peroxide, and ear cleaner also. Okay, hydrogen peroxide bottles, no, it is stored in plastic bottles instead of glass ones, because what happens with hydrogen peroxide is it is very unstable liquid. Okay, so with this you will be learning hydrogen peroxide separate concentration term, because molarity, normality, these are normal ones, right? But hydrogen peroxide is unstable liquid. So look at this will dissociate into water and oxygen easily, very easily. Even glass surface can catalyze this reaction. Even the dust can catalyze this reaction. So that much sensitive it is. It easily undergoes decomposition. Okay, so for that reason, what we define is a new concentration term, that is volume strength. Okay, volume strength basically will define it. No, what is volume strength? Because molarity we know, normality we know, but what is volume strength? Volume strength is simple. Okay, H2O2 is giving oxygen. Okay, now volume strength is defined with respect to this oxygen volume. What we can simply say is number of volumes of oxygen. Volumes of oxygen. It may be weird, no, to use volumes. You can use milliliters because volume units. You can use meter cube, you can use centimeter cube or ml, or you can even use liters. Okay, how many liters of oxygen, how many volumes of oxygen liberated per one volume of H2O2. So that must be at STP, number of volumes of oxygen liberated. Very important. This is at STP. STP conditions, anybody knows? I think everyone knows, right? What is STP? Standard temperature pressure conditions. STP. Sure. I hope now it is getting adjusted. No, voice is clear, I think. STP conditions, no, temperature, standard temperature and pressure. Temperature is what? See, 273 Kelvin. Pressure is how much? 180. So volume strength means how many liters of oxygen liberated per 1 liter. You can say, suppose X is the volume strength. Okay, Let us take X is volume strength. X is volume strength. Okay. So what is the meaning of this? So X liter of O2 at STP, okay, liberated by 1 liter of H2O2. Okay, per 1 liter, how many liters of oxygen is liberated? That is its volume strength. So more is a volume strength, more concentrated the H2O2 is. Okay, so now we'll simply convert this volume strength into molarity or normality, because see this, this question is talking about normality. This is the strength. What is the volume strength of 1.5 normal H2O2? So let us quickly calculate this. H2O2 gives H2O plus half O2. And we know that 1 mole is giving half mole oxygen gas. No, it is a gas. Oxygen is gas. So there is no doubt for everyone, right? Oxygen is a gas at room temperature. Fine. Now even at STP, this is a gas. Now, how much volume occupied by this gas at STP? Half mole. Half mole means how much volume? Avogadro volume number is there, right? 1 mole means 22.4 liter. Half mole means how much? So this is basically 11.2 liter at STP. 1 mole means 11.2 liter. Okay. Now we are relating molarity with volume strength. Okay. Now X liter of O2 at STP per 1 liter, right? Now highlight these terms, no? X liter of O2. So what I'll find is per X liter at STP, how many moles it is? We know 1 mole, 11.2 liter. Now X liter, how many moles? This is just unitary method, no? So moles of H2O2 is how much? X by 11.2. Volume of H2O2 is how much? Volume of H2O2 is equal to 1 liter. This is by definition, by default, no? Volume strength means X liter liberated by every 1 liter. So moles and volume is given. So molarity is simple now. Molarity is equal to moles by volume in liter. So molarity is X by 11.2. So what is normality then? Normality is always, no, for H2O2, it is 2 times 2 into X by 11.2. You may ask, no, sir, why you multiply with 2? Because see this equation. See this equation. And how many electrons are involved in this? How many electrons are involved? Oxygen oxidation number is -1. Okay. And this goes to 0. -1 to 0, but 2 oxygens. So if it goes from -1 to 0, 1 electron lost. Okay. But 2 oxygen atoms, 2 electrons are involved. So this is why I am multiplying normality is equal to 2 into X by 11.2. So that I can say like X by 5.6. So this is our relations, no? Molarity, normality, and volume strength. Normality equal to X by 5. What is X? X is volume strength. We defined it, right? See, look at this. X is volume strength. We defined. Clear? Fine. Now let us come back to the question. Okay, let us come back to the question. These are our useful formulae. We must know this, no? Then only we can find out volume strength. Normality is given. X we need to find, right? See. So normality is equal to X by 5.6. Normality is given, right? 1.5 is equal to X by 5.6. So X is equal to 1.5 into 5.6. How much it is? What is the correct option now? Tell me what is the correct option? exactly, 8.4. So these are the relations. If you know the relation, you can just do in within 30 seconds you can solve. But if you have to know the relation, what is hydrogen peroxide volume strength? Okay, we discussed here. Okay, and what is molarity normality relation? This one's, we must know this. Molarity is equal to x by 11.2, normality equal to x by 5.6. X is a volume strength here. Okay, fine. Okay, let us move on to the next question now. See, look at a very simple question here. Very simple question in organic chemistry. Okay, number of sigma and pi bonds in pent 2-ene 4-ine. I hope everybody is able to draw the structure of this and tell me for the means. Don't take the choices. No, first time only you should give correct answer. Pent 2-ene 4-ine. All of you please try and give correct answer in the first attempt. Don't take more than one attempt. Okay, easy question, but most of the students know what they'll do. They ignore some bonds. I'll tell you, just try this. Is it done? What is the correct answer? Everybody should get the answer. No, pent 2-ene. In the first attempt, you should give the right answer. Pent 2-ene 4-ine. So pent means 5 carbons. Let us write 5 carbons. 1, 2, 3, 4, 5. 2-ene. Second position, there is double bond. Okay, fine. 2-ene 4-ine. 1, 2, 3, 4. No, 4-ine. So how many hydrogens here? One hydrogen. Carbon must complete 4 bonds. Okay. Here all carbon bonds are filled. No, full. Next, but here 3 bonds only. Put 1 hydrogen. 3 bonds, 1 hydrogen. 1 bond, 3 hydrogens. So this is basically our compound, right? Pent 1, 2, 3, 4. 2-ene 4-ine. Now how many sigma bonds? Okay, first bond is sigma, right? So how many sigma bonds here? Look at this. First we'll count, no, CC bonds. How many CC bonds? How many CH bonds? Sigma. Because pi bond is not possible with hydrogen, no? Only sigma bond is possible. So first let us count CC. How many carbon bonds are there? 1, 2, 3, 4. 4 bonds CC. How many CH bonds are there? 3, 4, 5, 6. Anything extra here? Just check. Are we missing anything? No, right? 10 sigma exactly. Okay. Now more than one bond is present, then they must be pi. They must be pi. No? Here 2 pi. Here these bonds, no, pi bonds and this bond. So 10 pi bonds. Sorry, 10 sigma bonds. Okay. 3 pi bonds. Okay, so 10 sigma 3 pi means we must know structure, then we can easily do it. Done? Okay, so very simple question. How are we doing this? By just knowing carbon valency. Only by knowing carbon valency we can quickly distribute the bonds, but hydrogen can never form pi bond. Make sure, no, you don't form hydrogen pi bond. Okay, fine. Next question. Next question. Try this now. State of hybridization. How do you find hybridization? What simple trick you have? Please try that. Okay, are you done? So what trick you are using, tell me, for finding hybridization? Hybridization. Okay. See, look at this. I'll tell you very simple trick. Hybridization can find very easily. Hybridization is equal to, see, simple number of sigma bonds. Only take sigma bonds plus lone pairs. This is applicable to any atom. If you know the structure, just look for sigma bonds, and if there is a lone pair, you count that lone pair also. That will give, that number, suppose this number will give us 2, then sp hybridization, 3 sp2. If this number is 4, sp3, like this. Okay, now C2 carbon, just look at C2 carbon. Where is C2? Yes, no. So what you can do is you write like this question, no? Double bond CH2. Okay, so like this, one second. CH, okay, and H. Is there a triple bond like that? Double bond only, right? Think it should be triple bond CH, like this. Okay, so now 2, second position. How many sigma bonds are there for second carbon? How many? Yes, that should be triple bond. Okay, fine. So look at this. How many sigma bonds are there for second carbon? 2, right? Right side and left side 2. So number of sigma bonds are 2. And there is no lone pair, no? All 4 bonds are used. All 4 valences are completed. So 2 must be sp. C2, it is sp. Now look at C3. How many sigma bonds? For C3, how many sigma bonds? Check the structure. Check the structure. How many sigma bonds for C3? Four, right? Exactly 4, right? Okay, so 4 means sp3. There is no pi bond, no, for C3. So C5, look at C5. C5, 1, 2, 3. So only 3, because there is double bond, means only one sigma, and other one is pi. Other one is pi. So C5, there are only 3 bonds. One is CH, other 2 are CC bonds. So SP C6. C6, all four bonds, sigma bonds. So sp3. So sp, sp3, sp2, sp3. Option D. Option D. So always use this. It is very simple. If you know the structure, hybridization you can find by using this. If structure is given, number of sigma bonds plus lone pairs. If structure is not given, we already discussed in the first class itself. Chemical bonding chapter, while discussing that, we discussed, no? If nothing is given, no structure is given, finding central atom, then valence electrons, that method you can use. Okay. Moving on to the next question. Look at this. This is about tautomerism. Okay. What exactly a tautomerism is? Okay. Tautomerism is special type of structural isomerism. Here, structural isomerism basically means bond breaking and making takes place in structural isomerism. Connectivity is different in structural isomerism. So one of the types of structural isomerism is tautomerism. So this is basically, hydrogen transfer between carbon and other electronegative atom. Or simply, most common, there are many other positions also possible tautomerism, but most common is 1,3 hydrogen transfer. Very simple way we can define 1,3 hydrogen transfer. Okay, 1,3 hydrogen transfer is one of the most common types of tautomerism. That is what we all search. But sir, do we have only 1,3 hydrogen transfer? No, there are other types also, but 99% cases, no, tautomerism is very common. 1,3. What is 1,3? Just count from oxygen position. See, there is a ketone. Okay, ketone. And what you have to check is CO group must be present here. Okay, and there is hydrogens. So these red color ones are called alpha hydrogens. Okay, because CO group is our functional group here. This is keto group. Okay, and this is also called, in tautomerism there are different names are given. This is called keto form. So two forms are always in equilibrium. Okay, two forms always in equilibrium. Equilibrium means both the isomers are existing. Both isomers are existing and they are in equilibrium. One form is converting into other form. So keto form will convert into enol form. Enol form. See, en plus ol. Double bond means en. Ol means OH group. Okay. Double bond means en. Ol means OH. Okay. Now we can transfer like this. No? H can be transferred here and double bond can be shifted here. So what will happen here? See, I'll show you with those colors only. Double bond and hydrogen simultaneously they get transferred. O, and there is H. Okay, H here, H here, H, H, H. And keto form and enol form both are in equilibrium. So what is the condition for this tautomerism? There must be alpha hydrogens. Without that, no, tautomerism is not possible, right? So what you have to see is you check for alpha hydrogens. What is alpha position? It is next to CO group. This is alpha position. No? This is alpha position. So alpha hydrogens you are shifting in keto form. Enol form, what you are doing? You are shifting hydrogen from oxygen to carbon. Both are in equilibrium. So reverse also you can do. You can do the reverse way also. Hydrogen to carbon, double bond to oxygen. But here double bond to carbon, hydrogen to oxygen. So these are in equilibrium. Now look at the question again. Which of the following molecule where alpha hydrogens are present? Just check. Is it done? Okay, so where are alpha hydrogens? Can you tell me? Okay, so which of the following molecules? They're saying 1 and 3. Are you saying 1 and 3? Okay. Can exhibit tautomerism? See, look at this one. There are alpha hydrogens. Yes, there are alpha hydrogens. Okay. Here, there is alpha hydrogen. Okay. Here, is there an alpha hydrogen? Yes, 3 bonds are there, 1 alpha hydrogen. Okay, fine. But remember, there is one more rule. In bicyclic compounds, it is what Brett's rule. Brett's rule. Okay. According to this rule, double bond is not possible. Double bond is not possible at bridgehead position. So what is the meaning of bridgehead position in bicyclic compounds? In bicyclic compounds. See, if you see, this is a bicyclic compound and bridged bicyclic. Okay, you can't have no double bond at this position. So this is not possible because bridgehead positions are no, these are bridgehead positions. So the actual meaning is you can't bring these two atoms in the same plane because bridged ones are very rigid system. Bridge system is very rigid, so you can't have no all the carbon atoms in the same plane. So that is why, so that says, the principle says no, bridge rule says you can't bring two bridge head atoms into the same plane. Okay, so that means very simple. Now you can see the options again. Double bond should not be possible. Okay, at bridgehead positions. But look at the three compounds, three bridged bicyclic compounds, no, where you get double bond at bridgehead position. If you are getting double bond at bridgehead position, so it is not possible. Tautomerism is not possible. You can't write double bond, right, at bridgehead position. So check that. Okay, check this. So here double is possible, but where? Only at bridgehead position, no? Only bridgehead position. In 1, only bridgehead position. But in 3, yes, this is not bridgehead position. I'll write it, no? This is not bridgehead position. This is possible, but this is not bridgehead. See, double bond OH. Now this is not bridgehead position. This one. But I'll show this with the red color. Now this is bridgehead position and there is no hydrogen here. So only one possibility, 2 is not possible, right? And this is not possible. Bridgehead positions, you can't have double bond. Understood? So full answer. So I'm marking all the places. Siddharthan. Okay. So just check this. No, you can't have this. If you write, no. So one of the position I'm writing, see, look at this. You can't have molecule like this. So this is OH and double bond, which is not possible. This is bridgehead position. No? You can't have double bond. So same way, 1 and 2 are not possible. But yes, 3, can you can shift this hydrogen because this is not bridgehead. No? So final answer should be C. Can exhibit, sorry, can exhibit, right? Cannot exhibit means 1 and 3. So can exhibit means only 3. Only 3. 1 and 2 are not possible. Very, very important question, no? If you see in bridgehead means bridged bicyclic compounds, we have to make use of this Brett's rule. Okay. Understood? I hope you got clarity, right? Okay, fine. Next. Now this is a very interesting question, no? How many structural isomers are possible when one of the hydrogen is replaced by chlorine atom? So this is from basic organic chemistry isomerism. How many structural isomers, not stereo, only structural isomers, when one of the hydrogen is replaced by chlorine atom? Every time you have to replace one hydrogen only. So let me do by a systematic way. There is one group, one phenyl group. Okay, I'll replace here. Only one hydrogen I should replace, right? So this is one. This is one. One possibility. Okay. Second one. So these positions, no, see this position, this position, this position, this position, all are same, right? 4 positions are same. So I can write this one. Okay, this is chlorine, this is CH2, because all 4 positions are same. If you replace any of the position, you will get this. No? Right. Next. So you can think of other positions, this position, this, all are same again, right? Okay. So let me show you here. No, here you will get clarity. This positions, they're same, right? So you can replace them anywhere. If you replace one hydrogen, you will get same isomer. So this is CH2, and every time you have to replace only one hydrogen, not all hydrogens, no? Only one hydrogen. So this is chlorine. Sir, why are you using only left side ring? No, you can use right side ring also. Just look at this. This is CH2. This is CH2. This is CH2. This is CH2. Just bring this with this color. Same color means same position. Okay. Okay. Now, what is another isomer? This one. Chlorine, CH2. This. So how many maximum structural isomers by replacing hydrogen here? B. 4. Just look at this. If any doubts, please let me know. No doubts, right? Shall we proceed? Okay, just look at hydrogen replacing. Either you select left side ring or right side ring, it will be same because both are symmetrical, no? They're symmetrical. So one by one, systematic way, start from the middle one. Okay, then go systematically replace each and every hydrogen and check. Okay, done. So we'll move on to the next question now. Okay, next question. See, look at this question now. Number of isomers in C4H10O. How many isomers? How do you write systematic way? Okay, but we should know what is the functional group in this. See, C4H10O, O can be present in different functional groups. No, if O is present, I can say it is alcohol. Okay, or it can be ether. Okay, it can be aldehyde, it can be ketone. There are many possibilities in which single oxygen is present, right? It can be enol. This is also possible. But how do we know this? We have to write all possibilities, right? So listen carefully. Listen carefully. I'll tell you one simple trick, very simple trick to restrict, means again to do in a systematic way, to select a functional groups, to select proper functional groups. No? What we can do is you find number of hydrogens. Okay, see, this is what, no, degree of unsaturation. Degree of unsaturation, you can say, means to know whether this contains double bonds or single bonds. If it is no double bond, no, if it is no double bond, we can eliminate these options, right? These options contains double bond, but these options contains only single bond. You can eliminate the options, right? Very easily. So that is what we should find, degree of unsaturation. What exactly is it? How many hydrogens in saturated compound? Let me write here, degree of unsaturation, or this is called hydrogen index. Okay, sometimes it is called as, no, hydrogen index. So based on number of hydrogens, we can find this compound is saturated or unsaturated. Okay, degree of unsaturation, or also it can be called as double bond equivalence. Okay, so there are many names for this: double bond equivalence, DBE, DU, degree of unsaturation, hydrogen index. So this is basically number of hydrogens in saturated compound, okay, minus number of hydrogens given. How many hydrogens in saturated and how many hydrogens in the given compound by 2. But first one, how to do this? Number of hydrogens in saturated. We know this formula, no? Saturated means n carbons can accommodate maximum 2n plus 2 hydrogens. Everybody knows this, no? Because saturated hydrocarbons are alkanes. So we must know this, no? N carbons are present. There are 2n plus 2 hydrogens. Okay, fine. No. Now look at this. 2n plus 2 means 4 carbons are there. 2 into 4, 8. 8 plus 2, 10. So 10 for this compound. Degree of unsaturation is how much? 10 minus. How many hydrogens are there here? 10. But sir, oxygen is there. You consider oxygen as 0. Okay, very simple. It looks like 0, right? No, just a symbolic, you know. But we should consider oxygen as 0 only. So 10 minus 10 by 2. So that's 0. There is no double bond. No? All are single bonds. C4H10O, all are single bonds. Now let us write, no? we have left with only two possibilities. It can be either alcohol or ether. Okay, either alcohol or ether. We have only these possibility. We don't consider this. No. There's no double bond. Okay, so alcohol and ether. So let me write one by one, but again systematic way. So 1 2 3 4 and saturated OH. No? All isomers, right? One OH. Second one, how do you write? 1 2 3 4. See, each dot here represent carbon. This is bond line formula. Okay, so 4 carbons here, and now I changed OH position. OH position. Okay, 1 butanol it is, 2 butanol. Next one. Now what I'll do, 4 carbons chain is over. There's no other possibility, right? So 3 carbon chain. I'll write 1 methyl here, 1 OH. This also gives same formula, no? Next, this one, CH3OH. Systematic way, see, 3 carbons in the main chain, 1 in the branch, like this. Next, how many we get? Count. 3 carbon once is over. Okay. Is there any other possibility? 3 carbons. If you write OH here also, you will get same, no? OH3 methyl group. Done. Now 4 carbons, 3 carbons. With 2 carbons, can we write 2 carbons? Try writing this, no? 1 2 3. Again it is same OH. 2 carbons, no? Not possible. Write ethers, no? Write ethers. 1 2 3. 1 2 3. O. This is ether. Okay. And now next. 1 2 3 carbons one side, 1 carbon other side. Okay, this is 1 ether. But now you can write other ways also, like this also you can write, no doubt. 2 carbons, 2 carbons. Okay, and when you write 1 carbon, there is one more ether you can write. This one. This is also different one, right? So this is how you should write systematic way, no? Number of carbons, how many carbons, left side, right side to this oxygen. So maximum how many? So there are 4 alcohols, 3 ethers. So we should get 7, right? Is there any 8 possibility? Do we have any other possibility? Just check. No, please check. Do we get? Because 8 is also one of the option. No? Do we get such possibility? No, right? Check carefully. Alcohols, 4 carbons, 3 carbons, just count this. No other possibility, correct? Okay. Everyone agree with this, right? Carroll Center, see, they are asking only structural isomers. If enantiomers are there, then we can count, but only structural isomers. See this, no? That is what I said, no? Only a number of isomers they are asking. Okay, okay. Then Carroll Center is different thing. We'll discuss later, because Carroll Center, we have to check Carroll Centers. Yes. So if you check Carroll Centers, let us discuss now that also. Okay. Here, I don't think option will be there, but see, let us check this Carroll Center. Okay, this Carroll Center means 2 possibilities here. Okay, here there is no Carroll Center because methyl groups are same, but here this is not Carroll Center. Okay, fine. Next, any other possibility? No, right? One, two, three methyl groups, no chiral center, four different groups. So one pair of isomers. So it must be mentioned actually structural or total isomers. So it should be 8, no? Including this includes, no? Includes stereoisomerism. Okay, includes stereo. But if it mentions structural, we are looking at structural actually. Okay, fine. So you have to take that isomer also. Chiral means two enantiomers. Okay, means these are basically stereoisomers. Connectivity is same, but arrangement can be different. No, such like this. This can be OH. No? One is up or one is down. This is possible. Chiral center. Four different groups compulsory. Okay, so if four different groups are there, that must show optical isomerism. So our final answer should be 8 because they have not mentioned any structural here. Total number of isomers, total isomers will take. Okay, fine. Next question. See this. Which of the following carbocations expected to be most stable? Most stable here. But what is NO2? See, look at the structures here. If NO2 group is there, remember this, or NO2 or any resonance group, ortho and para positions are most important. Okay, ortho and para. Now, if you have minus M group, or this is also called as minus R group, so that will destabilize carbocation. Destabilize carbocation. Or I'll write it. Very, very important point it is. Very simple way we can eliminate options. Ortho para positions are very important with respect to the group. Okay. If in ortho para positions, minus M or minus R group, okay, carbocation stability will decrease. Okay. But plus M or plus R group, stability of carbocation will increase. Very simple. Okay. But NO2 is no, NO2 is strong withdrawing group. It is strong withdrawing group. So ortho position or para position, that will strongly decrease carbocation. Okay. Now see this ones, B and D options. Why it will decrease also I'll explain. So let me write B, expanded structure. I'm writing B. Okay. This is B option. Let us see. This is plus N. NO2, if you write NO2, there is positive charge on nitrogen. So look at this carefully. Two plus charges on adjacent atoms, which is not acceptable structure. Or the energy is very high. The energy is very high. This is least stable. Okay, so this is least stable because nitrogen and next carbon is positive charge. Next carbon positive charge. So B and D directly you can neglect. B and D directly you can neglect. Understood? Why are we neglecting this? Why are we neglecting? Because nitrogen adjacent carbon has positive charge, no? Positive charges on two adjacent atoms, which are not possible. Okay. Now A and B, A and B, A and C, A and C, this is least stable because I already said no, ortho para. Now this is para position, right? Para to NO2 group. This is ortho, meta, para. Okay. O, M, P. This is para. So with respect to para, NO2 is present, no? Stability of carbocation will be least. Now meta, this is most. In A, B, C, D, okay, B, C, D are less stable or least compared to A. Understood? So this is how you should eliminate options when comparison of carbocation stability, comparison of carbanion stability. Just check this rule, no? Very simple. Ortho para position. Just check ortho para position. If it is carbocation, this is the rule. Carbanion is opposite, no? Carbanion is just opposite. Okay, fine. So next question. Which one of the following is most reactive towards electrophilic reagent? So what does that mean? So you have to choose option which is more nucleophilic. So if electron density is more, electron density on the ring is more, so that is more reactive. Because if it has more electrons, then only it will easily give electrons to electrophile. No? If electron density on the ring is more, that is more reactive towards electrophile. Now, how do we find this electron density? See this one by one option. No? CH3 group. Okay, we have 3 electronic effects. What are those electronic effects? Resonance effect. So higher priority, top priority. Next, hyperconjugation. Alpha hydrogens ones. If more alpha hydrogens, more is hyperconjugation. More is a releasing effect. More is resonance plus R resonance. Basically, that increases reactivity. Hyperconjugation increases reactivity. Inductive effect plus I effect. Hyperconjugation is always releasing. Okay, so hyperconjugation plus, if plus is there, no, they increase electron density. That's how they are more reactive. Now, which one is more reactive in this? So look at this one by one. Hyperconjugation, because alpha hydrogens are there, hyperconjugation. This is giving electrons. Now this one has resonance because oxygen is directly attached. No, there is plus R group. Here hyperconjugation, yes. Okay, this alpha hydrogens, and this is also giving, but by resonance. Now A, B options, if you see, both have hyperconjugation, both have resonance, but which one, for which structure more resonance is possible, OH or OCH3? Look at this. Resonance is same, sir, because oxygen atom is there. No, fine. Yes, exactly. And there is another effect. No, OCH3, CH3 group can show plus I effect also. But here there is hydrogen, no hydrogen, which is neutral. Okay, which is lacking in option B. There are 3 effects. Inductive is there, resonance, hyperconjugation, but hyperconjugation resonance only because H is neutral. It is not releasing, basically, not withdrawing. So, but this is also resonance, but here there is no resonance. OH is separated by another carbon, right? There is no resonance, but this resonance is very weak. This is involved in resonance with this also, CO group. CO group is withdrawing this. So competition between A and B, A wins because CH3 plus I group, oxygen resonance, CH3 also hyperconjugation. A is most reactive, more resonance, more plus R group, more electron density, more reactive it is. Okay. Now look at this separation methods. Which one is correct? Orthoparanitrophenol. Orthonitrophenol is this one. Very important separation method. How do we separate in lab? No? Orthonitrophenol, paranitrophenol. Okay, this is a structure. No, this first one is orthonitrophenol, paranitrophenol. Which separation method we use? Do you have any idea about this? Listen carefully. This has hydrogen bond. Okay, but this has intramolecular hydrogen bond. Intramolecular hydrogen bond, but this has intermolecular hydrogen bond. Between the molecule it has hydrogen. Within the molecule orthonitrophenol has hydrogen bond. What will happen? Now this orthonitrophenol, it cannot attract another orthonitrophenol, because in the orthonitrophenol itself, these groups are bonded, no? So within the molecule, hydrogen is trapped here. It cannot attract another molecule. So if it cannot attract another molecule, its boiling point decreases. Okay. So I'll write here molecular attractions, no? Low molecular attractions. Okay. Boiling point is very low, but high molecular attractions. Why high molecular attractions? Because this H is free now. This can attract with another NO2. Okay. And boiling point is high. Para-nitrophenol has high boiling point. Orthonitrophenol has low boiling point. So which method we use? Boiling point difference, no? Usually we use distillation, but steam distillation means we pass steam also. That steam take away orthonitrophenol vapors. We heat the mixture which contains ortho and para-nitrophenol. Okay. So we heat it. And steam will carry away ortho ones only. So steam plus orthonitrophenol. This is how orthonitrophenol is separated from paranitro. Paranitrophenol cannot be easily converted into vapors because its boiling point is high, relatively high compared to ortho. It's very simple, right? Steam distillation. Let us do this question, practical organic chemistry. Nitrogen detection in organic compound is carried out by Lessagnes test. So what is the blue color? Means what happens is in organic compound, okay, if it is giving no blue color in Lessagnes test, this is called no Lessagnes test. So that confirms no, if any organic compound it is giving blue color, so that must contain nitrogen. So this is laboratory test to detect nitrogen. Okay. So what basically we do, what reactions are involved here? Organic compound contains carbon, nitrogen. We heat with sodium basically in Lessagnes test. Okay. Lessagnes test, what we do is we heat with sodium. So what will happen? This will form NaCl. So cyanide ion will be formed. Because organic compounds are covalent, right? It will not give test easily. So we are converting into ionic compound in Lessagnes test. Now this Cn minus, okay, this Cn minus plus, we add iron sulfate. Okay, so this iron sulfate and some of the iron plus 3. Iron sulfate actually, before this what will happen is iron sulfate, some of the iron sulfate react with H2SO4. We also add acid, concentrated acid. So that will give Fe2SO4 3. Okay. So that is basically giving, no, you can write like this, very simple way, concentrated H2SO4. So what is happening here? Iron plus 2 is converted into iron plus 3. Okay. Some of the iron plus 2, not the all. We add very less, no, 1 or 2 drops of iron concentrated H2SO4, just 1 or 2 drops. Some of the iron plus 2 converted into iron plus 3, not all. So now what will happen? We have iron plus 2, Cn minus plus iron plus 3. So this will form a mixture, no? Fe Cn 4 minus plus iron plus 3. The iron plus 2 actually forms a complex, coordination complex with this. Now these two will combine and gives a beautiful blue color, intense blue color. So Fe3 and Fe4, FeCN6. So this is how we should write, no? Fe plus 3 and FeCN6 4 minus. Okay. So when they combine, 4 comes here, 3 comes here, Fe4 FeCN63, that is called Prussian blue, intense blue color. So this confirms nitrogen. This is the test to detect nitrogen in organic compound. Okay, very, very important. Fe4 FeCN63. So what is happening here? So we again discuss this. No, look at this point. Whatever nitrogen present in the organic compound is converted into Cl, NaCl, and we add very small amount, 1 or 2 drops of concentrated H2SO4 to iron sulfate, and we mix this solution. Okay, so iron plus 2 is present with Cn minus, it will form FeCN64 minus. It forms a complex with iron plus 2 oxidation number, and this combines with iron plus 3, which was formed with concentrated H2SO4. Okay, so this will give intense blue color solution that confirms nitrogen. Okay, so with this we are ending the session today. I hope everybody liked the session and learned new concepts today. Yes or no? I hope yes, right? Okay, thank you. You can see, you can join that WhatsApp group. Okay, if you want to contact me, okay, join the WhatsApp group. Schedule will be given, daily schedule. And please don't forget to share your feedback. Recordings, I think they'll be provided in that session. Thank you very much. Thank you everyone. WhatsApp group link also will be given to you. Okay, sure, we'll send this PDF. Okay, thank you so much. So we'll meet in the next class with few exciting concepts. Okay, take care, stay safe, stay healthy, stay safe. Okay, bye.